thing we've done is that potential of the straight rod, right? Is that pretty much the last thing? So that's going to motivate the absolute angle discussion, and that'll be a good way to get going. So I think, and these are the most recent homeworks. I'll do a big picture here. So we have minus L over 2, and we just have a linear mass distribution here. And then we're asking, what is, that's our x-axis, that's our point x. What's the potential like at this point x? Potential v equals minus integral em prime over r prime. This is just the symbolic form there. In fact, there's a g in front of it. At x much greater than L and at y much greater than L. So those are the things we were tackling. And what we find, and what you guys are going to prove, is that we have this v of x equals minus g m. Oh yeah, this thing was a length L, mass m. Right? Lambda was m over L. So what do we find here? We find minus gm over x plus something over x cubed. And for this one here, and you guys are just going to complete the whole problem, we find v of y equals minus g m over y plus something over y cubed. So this is what you're going to find. We actually found this one, and you're just going to complete that Taylor expansion. You're going to find that the 1 over x squared term is managed in both cases, over y squared. So what you have is, if you're far enough away from this object, y-axis is if you're far enough away from it, then it just looks like a point mass, regardless of its shape. If you're far enough away from it, because that's the potential of the point mass. Multiply it by lowercase m potential energy. So these are the correction terms. And on the other hand, we had to do a bit of work to get there, and these are only true on these axes. But what if you're out here at point P? Then you'd have your work cut out for you to do this. So this is going to explain, and we're going to do it completely systematically. This is going to explain the u of r equals minus alpha over r plus beta over r cubed problem and the absolute angle problem. So I think I'm going to work this one a few more steps right together with us. Anybody else done this one yet? Yeah, well, we're gonna try it right now. Okay. But this shows you where this term comes from, and we're gonna do a really systematic derivation of it. You already see right here, you're getting that 1 over x cubed, 1 over y cubed. And so for one thing, you realize that this is not a 1 over r cubed term that is true all the way up to the origin. This one, this one is true for all r. This is a perturbation of sorts, and it's really only true, as you see when we do these expansions, only true for, like I said, x much greater than L, so greater distances. Okay. So anyway, let's look at the absolute angle. This one's really interesting, and just for the reminder, the absolute angle for nearly circular any orbits, but for nearly circular orbits, it's the angle swept out between R min and R max. That's a pretty bad picture, but that's the angle swept out. For the Kepler orbits, it's actually equal to pi, right? It's equal to pi because those are closed orbits, but generally speaking, it doesn't have to be equal to pi. So this was a very nice problem. And we had derived a formula. C was equal to pi over root 3 plus R U double prime of R. I could write R sub 0 U prime of R. That would be the radius of the circular orbit. And the radius of the new radius of the orbit with this extra term here is going to be a smaller orbit correction, so we didn't have to worry. We can essentially keep the original orbit R sub 0. So what else do I have to say about this? This expression only uses this potential here, whatever one we had. So don't make the mistake of somehow using the effective potential in here. The effective potential, yeah, we won't even put it down right now. Okay, this is just that effective potential in here. So we did this calculation. Good. So now we have to take a couple derivatives. So we have U prime of R. We get alpha over R squared minus 3 beta over R fourth. And then for U double prime, we get minus 2 alpha over R cubed plus 12 beta over R to the fifth. So it looks like this is going to be a pretty involved calculation. It simplifies a lot. So yeah, we're going to go into here with this expression. I'm going to clear up some more over here. So let's have a look here. So yes, set this up. I divided by 3 plus, and R times the second derivative, you'll notice it's going to give us the same powers as this one has. So it'll be negative 2 alpha over R squared plus 12 beta over R to the fifth. Divided by alpha over R squared minus 3 beta over R to the fourth. It looks like I made a mistake here. This is R to the fourth as well. Okay. Yeah, we got it. Yeah. Okay. So now we have to do a little bit of arithmetic. And what we do is we get a common denominator of alpha over R squared minus 3 beta over R to the fourth. So multiplying that over, we're going to have 3 alpha over R squared. There's going to be minus 2 alpha over R squared. We subtract that one out, right? 3 times this one minus 2 of those. So we're going to have alpha over R squared. Multiply this one over, we'll have minus 9 beta over R to the fourth. But we're adding plus 12 beta over R to the fourth. So we'll have plus 3 beta over R to the fourth. Okay. And what we do now is factor out, we're going to factor out alpha over R squared out of both of these, and then we'll just flip the thing. Okay, there's 1 over that, so we'll invert it. So we'll have an alpha over R squared factored out. And then we'll have 1 might remember in the lecture I had mentioned that this is the small quantity, right, that we were gonna use in order for this to be a small perturbation. Okay. So this is simplified nicely, because now these two cancel. And we have 1 plus 3 beta alpha r squared. And that r is just the standard circular orbit radius, 1 minus 3 beta alpha r squared. Okay. So there's our absolute angle. And you'll notice when beta is equal to 0, it's a very clear 1 times pi. Okay. So then what you see is that we can treat this as a small quantity and do an expansion. Okay. And so that's what you guys will finish off the problem with, and then that's something you can hand to the astronomers. And the way we'll do that is this: we'll say C of, so here's, just to keep things simple, what you do is let C equal 3 beta over alpha r squared, because that's a small, and let that be much less than 1. That's a small quantity. And then we have C equals pi root 1 plus Z over 1 minus Z. And what we're going to do is to C of Z equals C of 0 plus the derivative times Z. See how we're going to expand it? This is why these expansions are such an important theme. Everything we do, we're going to expand it to first order, and this is going to be pi, and this is going to be some small or some quantity times Z. And when you're done, then you replace it with the Z in there, and you've got the solution. That's a solution that just shows you exactly what it means. Okay, because you've got that small quantity, everything related to everything else, and it's just the linear approximation. And because these are in practice very small quantities, this is all you need. You don't need the next approximation. This is excellent. Good. So that was the one problem, and I wanted to talk about it now because I have one of these up my sleeve for the exam. So if you want to have done this one, and then we could have related ones that would be similar. Yeah, what do you guys think? Okay, this is your strategy for success. Small quantity, linear approximation. Very good approximation, because again, these things are small. The astronomers, they're just looking at micro quantities. Arc seconds, it's small. Good, so that's the one problem. And the other one I want to review today is actually a couple having to do with circular motion. So we have some of those, and we'll return them on Monday, talk about them. But okay, if I erase this, that's good. Central force and circular motion. So on the one hand, we did the central force formalism. So we had M R second derivative has this form here. So you have something in that form, that's the central force problem. Okay. And on analyzing it, we found that the motion is restricted to a plane, and that's why we went to plane polar coordinates. So we got this, and then I can say u of r is equal to minus f of r dr. Oh, sorry, not a, but r. We'll just leave the bottom one open. Arbitrary constant. You have your potential energy. And then we found L equals R cross M B equals constant. And then we use plane polar coordinates. And there was some problems that went along with this that we did. We did the pendulum, right? We did that pendulum and the tension, the string problem. I was just looking at that. I got a hand back on Monday. So that's the one thing here. And you have the plane polar coordinates. That's when you end up with 1/2 mr dot squared L squared over 2mr squared plus u of r equals E, right? And then you have, remember this, both of these came from the kinetic energy, and this is formally, that's why we call it formally a potential. U vector of r. So as important as that is, it's also possible to look at this problem here. R of t is equal to a cos omega t b sine omega t and 0. So that was a trajectory in space, an orbit. And what we said omega is constant. Okay? And A and B are also constant. A and B are constant. So this is a special case of, what about this one here? I think I assigned this one as well. Or close to it. Close to it. Suppose we had A cos phi of t sine phi of t and 0. Then if we were to take two derivatives of this, we'd generate a little more than we did on this problem. So this is the one I assigned, right? Two derivatives, etc. What I did was, for the assignment on this one, I said, show that this is a solution to a central force problem. And the important thing to realize is you don't have to go to the plane polar coordinates. These are still Cartesian coordinates, right? X, Y, and Z. If you had an instead of a constant, if you had a phi of t, then you'd have, actually, let's go ahead and do it. R dot would be minus a sine p of t, and then outside of the sine, p prime of t, b cos p prime of t, and 0. So you could just pull the phi prime out there. But if you did an acceleration here, you're going to get a little more than that. You're going to get minus a sine phi of t, b double prime of t, minus a cos phi of t. And then you already have the phi prime, but the interderivative here is going to give you phi prime of t. squared. And then here you're going to have b equals b of t, b double prime minus b sine b of t prime of t squared, and we got the 0 again. Okay, so we've generated a bunch of stuff. And there are actually two vectors hidden in here. So I'm going to do, actually before I do anything, stay silent. Yeah. Here's what I'm going to do. Minus b prime of t squared. I'm dealing with this one. A cos b of t. Same thing here. B sine b of t. And what's my second vector? I'm going to do plus b double prime of t, pulling that out here, and I'll have minus a sine b of t. Oh, I forgot the 0 here. Put the 0 there. Good measure again. So minus a sine b of t, and the double prime here, b cos b of t. 0. Okay, so this is a more general one, and unlike this angle just sweeping out uniformly, this phi is an unknown, undetermined function if we were doing some dynamics here. But now let's go ahead and simplify this again. So let phi of t equals omega times t. So if we do that, of course, that's bringing us up to the original one. And what that's doing is, you know, phi prime is equal to omega, phi double prime is equal to 0. So that's actually killing this second one here. One of these is a tangential vector. One of them's a radial vector. So what I've done here is just a more general version of what we had on the homework. So here we go. So with this, right, with phi equals omega t, you're down the top of the board. We have r of t equals minus omega squared, and then our original vector r. I'm going to go ahead and put that up here. Actually, I need this stuff here. I'm going to get rid of the blank colors. Omega squared r. Okay, so here's what we found. R, two derivatives. So the acceleration is equal to minus omega squared r. That's the result, and you know, you can play around with this for more interesting stuff. Right? There's more going on here, but under these circumstances, we get this result. And what you have to realize is this. If you just multiply both sides by m, what do you have there? First of all, you have Newton's law, and second of all, you clearly have a central force law. Okay. So part of the assignment was to show that this thing traces out the ellipse that's easily done. I probably did it, I may have done it in class. But yeah, here we have a force law that's a central force, because the whole point of the central force is you got some function of r and you got this r over r. And in this case, it's pointing back. So all we have to do is do this. Minus omega squared m r here, r over r. And we see that we've achieved that form. Right? I just multiplied by 1, but now I have the unit vector, the directional vector, and therefore that's my f of r. Yeah, so this is too good. Actually, the f of r includes a minus sign, right? So it's a detractive central force. So this is apparently the solution to an attractive central force problem, and you guys, with this force law, and therefore you can figure out the potential, it's going to be an r squared over 2 potential, right? And it's a solution that, you know, we just kind of guessed or invented or threw up there because it looked interesting. Solution to central force law is not going through the rest of the central force formalism. You can reconcile the two, it takes a little bit of work. But it's a central force law, it's a central force solution, and so it shares all those properties, the general ones. So, yeah, I wanted to bring that in so you can solve whatever else I asked you. I may not have asked you much more, but you definitely want to know this one. This here, this is even a little much for the exam, but okay. So what happens is, yeah, since we're working on this, may as well complete this. So here's the potential energy. 1/2 omega squared m r squared. Obviously, right? You just do the basic integral. The potential energy. And in fact, this, in linear oscillations, this would be K. Okay, so the spring constant. So yeah, the connections are nice. Anything else to say about this one? Yeah, and in fact, I think, I calculated the absolute angle for one of these in class, as I recall, and it was pi over 2. Right? You guys remember that? Pi over 2. And, oh yeah, so now I can come back to that. I'm going to erase all this stuff here, okay? Just to tie all these loose ends together. What we saw was that if we had A and minus A, B and minus B, this was an ellipse. I'd stay there. This was actually an ellipse. Unlike the Kepler ellipse that we kind of had to prove, this is one that's right on the surface, right? This is x, this is y, x squared over a squared, y squared over b squared, cosine squared of sine squared is 1. But you can see the absolute angles, you're going from the maximum to the minimum, or you know, go from the minimum to the maximum. That's why the absolute angle was pi over 2. So here, c is equal to pi over 2. So you can see it here. And before, when we hadn't seen this, you know, we calculated the value was pi over 2. Okay. So that, in other words, when we had done c equals pi over 3 plus r u double prime over u prime, right? That's when we had found that it equals pi over 2. Good, so that ties all those things together. We can still do, if we study this, we can still ask 1 or 2 questions about it if we want to. This is a good one. Okay, so where does that put us? Let me consult my notes here. well, the other review type of things we'll have on Monday then. Some other things on my list, but that's not, oh, there was one more I wanted to talk about now, before we get to the stuff on Monday. So this one has to do with cycloid. So this was an old homework problem. Period of oscillations of an object that's sliding around in the inverted cycloid. Okay. So I'll just write period of oscillations in the inverted cycloid. That one I may bring in next Monday, but I'll just remind you what we had going on here. This is usually when I state for the Lagrangian mechanics. But here we are, this is the x-axis, this is the y-axis. This is minus 2r, so we've got a radius r, so this is r times pi. And this thing exists as a parametrization. So we had x was equal to r theta minus r sine of theta, and y was equal to r cos theta minus r. And then when theta was 0, it was 0, and theta was pi, it was minus 2r, yeah. So that was the inverted cycloid. Now when we did this, remember we measured the length of the cycloid, it was 8r. Theta was just a parameter, but if we're doing dynamics, we put room for an argument. If we're doing dynamics, this is x of t and y of t, because something is sliding around in that thing. And therefore theta, is theta of t. And then if we want to get the kinetic energy, t plus u, so we have to do 1/2 mx dot squared, 1/2 y dot squared, and then we have to do mgy. Now next semester in Lagrangian mechanics, we'll be able to do these kind of things, not with the energy, but with the Lagrangian, and it will be for any number of variables, but this works for one variable. The thing is, so you've got the energy, and we want to get it into the form on this problem. We want to get it into the form E equals 1/2. I'm just going to use different letters. A theta, no, not even right theta yet. We want to get 1/2 a z dot squared plus 1/2 b z squared. And this is by expanding about a minimum. So this takes us to the theory of small oscillations. There's a few intervening steps. I'm not going to do them all right now. Okay? But the point is this: you've got this thing. You actually take all these things, chain rule, etc., and you end up with 1/2. A is still a function. Theta dot squared. Okay. You end up with E equals 1/2. I'm just going to write A of theta, theta dot squared, plus, I'll just write E of theta for the moment. Okay. That's what you end up with first. You want to get it into this form, because if you get it into this form, then what can you say? Omega squared B over A, like K over M, right? So this holds true regardless, once you have these things as constants. So, that one has a fit. There's some interesting work in it, but I just wanted to bring that up, okay? So it's definitely good for us to know the cycloid. I'm not sure what I would do with it for the exam, but cycloid is in play at some level or not. I could actually take it a couple steps and set it up and have you guys do it for the last couple of steps I got there. The point is, you do all these steps here and you're trying to go for this standard form, because remember this, E equals 1/2 M x dot squared plus 1/2 kx squared. Do you guys recognize that? That's the energy of your harmonic oscillator. And anytime something has this form, which is what this meant, then you can just cut to the chase and you know your frequency of small oscillations. So that holds true regardless what these letters are named, right? As long as you've got the form of the dynamical equations. So yeah, this is a really important one, right? You'll never see the end of the harmonic oscillator. Okay, good. So that's what I'm gonna leave it at. And I'm gonna start that problem with the potential expansion. Okay, we have a few minutes. This is pretty technical, but we'll get started on this. And then, on Monday, we can pull everything else together as well, and I'll hand it back. By the way, I can consult this page actually. So that central force one that I just talked about was due today. That absolute angle that we talked about was due today. Oh, nice. So the Newton's law looks like it came out. That must have been satisfying. Wasn't that bad. And then those natural log ones. Okay, good. That's a good set. That's a decent set, and I've done some work on it for you, so you shouldn't have a problem. Okay. So here's what we're going to do next. You want to get that formal expansion of the potential, and actually I was just realizing along the way that will give us a proof of the nature of the spherical symmetric mass distribution, right? The spherically symmetric mass distribution acts like a point mass, right? That we've been using that fact all this time. After all, if you're outside a spherically symmetric mass distribution that's perfectly spherical, and you're standing up here, right, then your weight on the scale is actually GMM over radius of Earth squared, right? That's making use of that idea. That Newton's law, that this entire body the Earth, you're standing on the surface, you're being attracted towards its center as though it were a point mass. But as soon as you don't have a perfectly spherical body, say this thing is rotating rapidly and it's distorted, then you no longer actually have this exact result, okay? So what we're going to do is consider the potential for an extended body that we did for just the rod. Okay, so we've done that thing with the rod, but now we have to go a step beyond that. So potential V of R, and the way to always look at that is minus G integral dm prime R minus R prime magnitude. And I'll show you in a picture what's going on here. What we do is we've now got this extended body. We're going to be away from it, and we put the origin at the center of mass. Okay. Center of mass, take our origin at the center of mass. This is the vector R, the point R, r away from the center of mass, right? So we're gonna integrate over all of the points of the body, so we could call this here an r prime. And then if this is a little point mass right here that we're integrating over all of them, then we would have this vector here. So this is our r minus r prime. And again, so we're integrating over all these point masses dm prime, so this is our little dm prime here. And you can see we integrate over the entire body, and the magnitude of the distance, r minus r prime, is the distance from that point mass to our point outside the body. Okay. Good, so this is well defined. This is just taking the law of a point mass and adding them all up. So you have to assume that the potential is that, okay, like that. So what we have to do now, I'm just gonna sketch the idea. We have to do an expansion. So this is an exact result, by the way. Okay, this would be the potential you do the whole integration over a solid body. Next, we want to expand this f of r actually, I'm not even going to state that. We're going to expand this thing here in a Taylor expansion for small r prime. Okay. For small r prime. Well, what does small r prime mean? That means that this magnitude of r prime is much less than the magnitude of r, because we're a reasonable distance, or a serious distance away from this thing. Okay. Small r prime. So here the question is, how do we do this expansion? And what I'm going to do is, this is something we've been doing in math methods. Suppose I had f of r plus r prime. And I'm going to expand around these small quantities being 0. Then we would formulate our Taylor expansion this way. We'd have f of r plus sum over f xi evaluated at r xi prime. Those are my small quantities now. The small quantities of my r prime. I equals 1, 3 plus 1/2 double sum jk e squared f dxi dxj xi prime xj prime. So this is what we're going to have to do for this function here. And what's going to happen is we'll be able to do the whole thing formally and go back into this integral and get some very general formula for it. But that's the strategy. So, you know, we often have an x minus x prime here, but we're doing it different this time. Okay? This is just analogous to, in one dimension, you know, f of x plus h equals f of x plus f prime of x h plus 1/2 f double prime of x h squared. So that's that type of a Taylor expansion. Good, we'll do that next time. Actually, we'll see. We may have to save that for after the exam. But, it's gonna be a great result. Over the sweat, I guess.